we will be seeing the data sheet as we discussed. So, what is the IC name again? It is DAC 7821. This is the part number of the IC, okay, that we are using. This is the digital to analog converter IC that we will be using, DAC 7821. So, now let us just see the data sheet. So, this is how a normal data sheet of any company or an IC would look like. So, they have I think you can see my cursor. So, they have the IC image here, this is how the IC will look like, and then in one line they will explain what actually this IC is. This is 12-bit parallel input multiplying digital to analog converter. So, in one line they have told us what is it actually. So, this is 12-bit. So, let us note it down. So, how many bits are there? 12 bits and parallel input. So, it is parallel input and multiplying type DAC. So, there are different types of DACs which you have seen and you will be seeing in the course, and so this is a multiplying digital to analog converter. In the data sheet also we will see how they have explained it. So, this is a 12-bit parallel input multiplying digital to analog converter. So, what does parallel input mean? So, suppose this is the IC and if it is 12-bit, so there will be D0 to D11, there will be dedicated pins for this like this. So, this will be parallelly inputted, okay, parallel input to the converter, digital to analog converter, and at the same time in one shot it will be converted to the analog value, okay, that is 12-bit parallel input. Okay. Now, that we have seen, this is the core description of the IC. So, let us see the features. So, when you open the datasheet, as I told, we will cover first this datasheet in quite detail, and then come back again and see quickly when you are seeing the datasheet what all things you should look at when you are seeing a new datasheet. That is the whole idea. Okay. So, these features will give you a quick view about what is the whole thing. So, the features, see, this is a supply operation. So, this is you should always make sure, see, it can operate only from 2.5 volt to 5.5 volt. Okay. So, you should never give a supply more than that. Okay. So, that is one thing. So, let us say you apply it to like 20 volt or something and the IC will go bad. Then fast parallel interface, 17 nanosecond write cycle. What does that mean? It means that when we give the input to the IC, like the data bits, the bits which needs to be converted to analog, how much time. So, the analog value that will be converted inside the IC would be stored in some buffer or a internal small flash which will be written, that value, whatever analog value is there, that will be written there. So, this is the time taken to convert the digital value, so it is something like that. So, that will be written on to it. So, next time you want to update the analog value, you have to latch on the new set of digital inputs. Still you latch it on, analog value will not change. Then update rate of 20.4 MSPS. MSPS is mega samples per second. So, this like it can take that much update rates. So, that many samples if it comes, it can keep changing it at that speed. Though 10 megahertz multiplying bandwidth, okay. Then the multiplying bandwidth in the sense, because we had seen the digital inputs, how they will look like each bit, if you want to see. So, each bit if you want to see, we saw it like this, one bit will be like this, correct, one bit would be having lower frequency like this, correct. So, in the conversion we have to multiply it with 2 raised to 0, 2 raised to 1 and all, right. So, this is how the multiplying type DAC will work. So, that bandwidth for taking into account these signals, the fast changing signals, is what they have mentioned in the data sheet. Okay. So, that is 10 megahertz multiplying bandwidth, then plus or minus 10 volt reference input. Okay. So, this is the input levels of the this is reference input, this is what, so this is what it means. So, plus or minus 10 volt would be like what are the values of your ranges, like 0 volt to 10 volt, or it can even be minus 10 volt, or it can even be minus 10 volt to 10 volt, and you can have. So, because this is 12 bit DAC, okay, this is 12 bit DAC, right. So, that means there can be up to 2 raised to 12 levels as we have learnt now. So, that is how much 2 raised to 10 is 1024. So, 1024 into 2 raised to 2. So, this will be 1024 into 4, around 4000, 1024 into 4, 4 is 16, 4096. So, 4096 levels are possible. Okay. 4096 levels are possible because it is a 12 bit DAC. So, that means that there can be from 0 volt up to whatever is the reference voltage. So, here it is 10 volt. This DAC will be able to give analog voltages with precision of 10 by 4096, okay, this much value. So, this will be in, like if you take it, it will be around in some millivolts per, in some millivolts per level. Okay. So, that means if 12 bit, right. So, 0 0 0 0 0 like that 12 bits will be there. So, for each change in bit here, it will update the voltage value by some definite millivolt. That is what this means. Hope this is clear to you. We have discussed this. Now, next, so low glitch energy 5 nanovolt second. So, the glitch energy is like suppose there is a delay in one of the bits getting updated to whatever value we have set. So, that is what is called glitch in very simple way. So, the what you call the time taken, volt second is energy, right. So, that energy consumed in that conversion, that is low glitch energy. And then extended so we have to, you can actually go back and check it in detail. Then extended temperature range. So, this is the operating range of the IC. So, it can operate up to 125 degree Celsius. 125 degree Celsius is usually called industrial grade temperature, and it can go up to minus 40 degrees. And then is the main thing, this is 20 lead TSSOP. TSSOP is the package, and 20 lead means there are 20 pins or 20 connections. So, it will be like this, and 20 leads will be there. So, maybe 10 on each side, 10 10. We will see the packaging information in detail. So, this is that package. So, when you are making any design, package, like while doing the board design, while doing the PCB design, we need to ensure what is a package, and accordingly we have to make footprints, we have to create footprints. What we have to create? We have to create the correct footprint on the PCB. So, let us say we make a PCB with this DAC, correct. We will place, this is the PCB. So, the IC will be placed somewhere, right. So, for this we need to know the package. So, this is TSSOP and 20 lead, it will usually call 20 TSSOP or TSSOP 20. So, 20 leads will be there, accordingly we have to create the package. So, this also you need to remember when you are making a design. So, we are always talking from your design point of view. So, next thing is what? So, we are going through the main features, right, main features of the ICs. This is very important to you, so that this is the way you should analyze the datasheet. Once 2-3 times if you look at the datasheet, then quickly you can go through these things actually. Then 12 bit monotonic. What does 12 bit monotonic mean? What does monotonic DAC mean? So, that means that when you go from, let us say if you take a 3 bit DAC. So, 3 bit DAC means 0 0 0 0 0, because 12 bit is very difficult to represent here, that is why we are showing like this. So, 0 1 0, correct. So, this is the increasing digital word, right, we have seen. So, if the corresponding analog voltage also only increases like this, keeps on increasing only up to say 15 volt, whatever voltage we have set, then there is a direct correlation between the increasing digital word and the increasing analog voltage. Such a digital to analog converter is called monotonic. Okay. Monotonic means corresponding to your digital word below, your analog voltage will only continuously increase. This is monotonic type. Okay. this is monotonic DAC, then plus or minus 1 LSB, LSB is least significant bit, okay, 4 quadrant multiplication. So, this is the internal logic that is there in the IC. Then power on reset with brownout detection. So, this is again the reset process, or like when it, so when it powers on the IC, it will go back to its native state. It will not show any random analog voltage, it will show the analog voltage of like say the 0000 digital word. That is what power on reset means. Okay. Then read back function, industry standard pin configuration, that is TSSOP. So, these are the main features. So, in the data sheet first they will show you the main features. Next what they will show you? They will show you applications. What are the applications? So, this is like for your general understanding. This is not necessarily important for you, because when you identify an IC, it is already understood that you know the what is your specific application. And if you are like, before you identify IC, if you are looking for like candidate ICs, which IC can I use for my design, at that point this section will become important to you. Let us say somebody suggests you, okay, there is an IC like this, why can't you use that for your application? You will have technical discussions with your colleagues, then they will tell, okay, this company has this IC, why don't you check it out for your application? Then when you look at it, they will tell you application. So, this section is for that. So, it can be used for portable battery powered instruments, waveform generators, analog processing, programmable amplifiers and attenuators, digitally controlled calibration, programmable filters and oscillators, composite video, ultrasound, like this. Okay. So, then this is a description. This is, I am not going to the full details of it, otherwise it would be like reading the data sheet to you. So, that is fine. So, these are whatever we have discussed, only they have discussed here. The reference voltage, the supply voltage, all those things. So, let us look at a block diagram that they have shown. So, the DAC is available in a 20 lead TSSOP package. So, what are the things? The VD is, the DD is there, VREF is there. VREF, we saw that VREF is what is here, plus or minus 10 volt reference input, then supply voltage is there, then they have a power on reset, then control logic. So, CS is what? Chip select. CS is usually called chip select. In most ICs, if they have a CS bar signal, it is chip select. And what does CS bar indicate? So, if you look at any IC's data sheet and if you see a bar on top of it, that means, if you see a bar on top of it, right, that means this is an active low signal. Okay. So, if any chip pin description has a bar on top of it, it is active low signal. What does active low mean? Active low means that the signal will be enabled, or the functionality of the pin will be enabled when the value of the signal is 0. So, that the complement of it, which is what bar does, becomes 1 and it becomes high. So, that is active low. So, what does active low mean? Active low means that the signal or that pin is active when it is low or 0. So, this you should understand, this is active low signal. Okay. And read write bar, okay, read write bar would mean that when this signal is high, so it is read, so it will be reading, and when the signal is 0, it is writing. So, with the same pin you can have both read or write depending on the value that you give. Okay. Then this is your data bus, which we have already discussed, DB0 to DB11, that means it is a 12 bit data bus, and that will go in as a parallel bus. There will be a latch. So, it is like a latch would be like a buffer that is there until the latch is again refreshed. This new values of this will not go into the latch, then that will be written into the register, and then the 12 bit R2R ladder, R2R DAC. So, you could have covered R2R DACs in detail. So, the 12 bit R2R DAC, 12 bit R2R DAC will convert it into analog voltage and we can see it, okay, and the output can be seen here. So, output is measured in terms of current, it is given in terms of current. So, if you connect a resistor on top outside that pin, you can actually see it as a voltage. Okay. So, that is the main. So, this is the first page of the data sheet, this is how it will look like. Okay. Now, next is, okay, now okay. So, this is the first page. Okay. Next is main thing, this table is right, this table is very important. This is what you should make sure that you do not mess with these values while you are operating the IC. So, main thing is what VDD to ground voltage, okay. So, minus 0.3 to 7 volt it can go over operating free air temperature range. So, we provided that it is free air temperature outside, what is the range, then digital input voltage to ground, it can VDD, where VDD can have plus or minus 0.3 volt fluctuation. We have to ground. Operating temperature range, we already saw this, minus 40 to 125. Storage temperature usually, so operating temperature for the IC to operate efficiently and faithfully, the operating temperature range should vary from minus 40 to 125 degrees Celsius, but it can be stored at a higher temperature and at a much lower temperature also, minus 65 to 150 degrees Celsius. So, this is like always storage temperature will be more than operating temperature. If you take any IC, always storage temperature will be greater than operating temperature. Okay. So, most of the ICs will be designed like this. You can open and check any data sheet if you want, it will be like this, storage temperature will be higher than the operating temperature. Okay. So, that is storage temperature. So, junction temperature, that is plus 150. What is junction temperature? Junction temperature is a concept from VLSI. So, your chip will have a package. I will quickly go through it. This is not actually within the scope of what we are discussing, but for sense of completeness. So, this will be the black color, you would have seen any IC, no, it will be black in color here, full black. Inside that you will have a small die. Okay. This is the actual logic, this is the actual chip, this is just the package, this is package. If you break it open, if some IC is like damaged, you have something, you can break it open and inside you will see a small package. It will be very small, it will be like 1/50th of this area, outside area, and from here you will see leads being taken out. Okay, this is the silicon wafer in which your design is built, whatever DAC design is there. These leads are then finally taken out like this as the package pins. Okay. So, this is what you call die. Okay. And junction temperature is a temperature on the die when it is under full operation. So, there are 3 temperatures. If you open any data sheet of any IC, you can see these 3: junction temperature, operating temperature and storage temperature. Usually junction temperature will be the highest because that is where the heat is getting generated, that is the point of generation. That is the point of generation of heat, junction temperature, then operating temperature and storage temperature. Okay. So, this you should understand very clearly because this is very important for any IC point of view, especially junction temperature is very important if you are having any design with some analog processors or analog digital processors, because there if it crosses, a lot of computation will be involved and processors or microprocessors, it is called MUPs. Okay. So, lot of computation will be involved, and if lot of computation involved, automatically the die temperature will go up. Okay. So, that time you should make sure that you are working within the limits of the junction temperature. Okay. And then ESD rating is what? Electrostatic discharge rating. Okay. So, that is like what is the highest voltage that you can use, I mean so that it does not get damaged with electrostatic discharge. So, they will always have this flag, they will tell that stresses above those listed under absolute maximum ratings may cause permanent damage to the device. Exposure to absolute maximum conditions for extended periods may affect device reliability. So, what they are telling is that if you go beyond these values, anyway we do not guarantee proper working, and even we are telling that it might even get damaged. Also, if you keep working at these limits, almost limits, though it may be it is told that it is at this limit also it is working, if you keep working at these high limits also, your performance will get degraded or it might even damage the device over time. So, you should always work within sufficient buffered limits within the maximum ratings. Okay. So, absolute maximum ratings is a very important thing. I will finally, once we are done with this, we will enumerate which are the main sections of any data sheet that you should go through. Okay. So, that you can keep it as pointer, you can keep it as pointer for yourself. and then quickly take that list of items and then check your data sheet every time you open a data sheet. Okay. So, now we have seen absolute maximum rating done, cool. Next is electrical characteristics. So, this also we have seen. Okay. So, like what is the output leakage, so these are very high details, we do not need actually when you are making design this much detail, we do not have to see, only see main things. So, gain error, leakage current and all, it is fine, that is okay. But what is your design point of view, what is the voltage reference range, it can go up to minus 15 volt to 15 volt, this is your reference voltage, this is the maximum and minimum values that will be taken to get your step analog step voltage, whatever we saw, right, 15 minus 0 by 2 raised to 3, 2 raised to 12 and all, that will come from here. Then input resistance, feedback resistance and all, this you should just keep this in mind. Then this is what I told when we told, right, that noise level things, logic inputs, what are the logic inputs, VIL, VIH, input high voltage, input low voltage. So, these are those things, those voltages, input low, input high, those things, okay, input leakage current, power requirement. So, the VDD for the IC to operate is around 5 volt, typical operating voltage, okay. Then AC characteristics, these are all very high technical details, because this is this is the results from their characterization, okay. What they will characterize everything, because they have to guarantee so many parameters in the data sheet, but many of these parameters we might not have to look at it when we are that much in detail when we are designing it. Only few things that we need to see what is the reference voltage, what is the VDD voltage, is there any specific resistance that should be connected, that much you can see and just leave it. Then later if you are having some issues, see basic things you need to be sure and then start working on it, maybe then you might feel some issues, then you can go and check the nitty gritties in the data sheet and to see if there is any small issues. Okay. Then these are those things, DSC glitch impulse, total harmonic distortion, output spot noise voltage, noise also we saw, right. So, they even characterize the noise voltage in the AC characteristics. Okay. Then what we will do, then they will also tell you timing information, what will be the once chips. So, I told you, right, this is that thing. Let us take a snapshot of this. Okay. So, I just took a snapshot of that, so that I can annotate it and show it to you here. Okay. So, we saw that chip select is an active low signal, correct. So, that is why when it is going low, the data is valid. So, that means data has been latched, till then the data will not be taken as a valid data. Then what happens, write is this signal is low, when this signal is low, that means it is a write. So, this data which is the DB0 to DB11 which we saw, correct. So, that will be latched on to the DAC and analog voltage will be taken, correct, and then that will happen, and then chip select will go high, invalid, then whatever data even if it is changes, no, it will not take it, only next time when this becomes low, that time it will take it as valid data, and then but that time it is read. So, these things you should see, when it is read, when it is write, this is high. So, this is a read, this is write, this is chip select is enabled, this is chip select is high. So, these things you should see. Okay. Next, so that is the timing requirement. Okay. Now, next, then there are a lot of things like related to digital things like setup time, hold time and all, we need not go into the exact details of that. Then setup time, load, hold time and all those things are there, timing requirements. So, for specific voltage ranges they have timing requirements. So, they have characterized everything and that they have put. Okay. Let us skip that. So, this is another main thing. Okay. This is the main thing, package information, pin out, it is called pin out. Okay. This is another thing that you should look at. Pin out, we should look at pin out. So, that will show you what is the package, how many pins are there and what are each pins used for. That is the main thing you need for your design. So, we have seen, so this is the pin out. So, there is data bus, DB is data bus. So, we will have from DB0 which is LSB up to DB11 which would be MSB, DB10 and DB11 MSB, correct. This is the data. Then we have chip select, read write, then VDD whatever is your VRF voltage, and then RFB which is a feedback resistor, and output is given in current. So, if you connect the resistor to it, you will see the it as then ground, very simple connections. Major thing are the data bus which is the data lines, the read or write, the read or write here, and then chip select. I think you can see my cursor, and then the data bus. So, I will let me go out from snapshot view. So, and then that is it, this much. This is the pinout description. Okay. So, this is the pinout description, it is clear to you, right. Then once pinout is shown, then they will show you description what are each things for. So, this is IOUT is DAC current output, then IOUT2 is DAC analog ground, ground is there, then DB11 to DB0 is your data bus, then CS as I told is chip select input active low, and then RW bar read and write VDD VREF, okay, DAC reference voltage, then DAC feedback resistor, establish voltage output for the DAC by connecting to external amplifier output. So, this will give you the output voltage of the DAC, okay. This is one main thing. Then they will show, then another thing that they will show in the data sheet is typical characteristics, okay. Typical characteristics, this you can just glance over it when you are trying to make only when you are having some issues you can come back and see it actually, like you try to see the output of the IC, and then you want to know whether this is actually correct or is it expected, then usually the data sheet will have typical characteristics which they got while they were characterizing the IC. So, you can just go through it. So, that is also okay, fine, this is not that very important. Then reference multiplying bang rate, supply current versus logic input, mid scale DAC glitch, these things we can avoid. Typical characteristics, okay, then that is done. So, linearity error, what is linearity error versus digital input code? Linearity error is what I told before, same thing. So, we have covered monotonicity right here, this is monotonicity, correct. So, in monotonicity also it can be monotonic in two ways. How? Let us see. So, I told you that digital input will be there and analog output will be there, and if it is monotonic it will be like this, but then it may still be monotonic, but it may be like this, or it may not be a linear relation. What is the linear relation? A linear relation is like this. The curve between the digital input and the analog output might not be a linear curve, it might be something like this. So, not exactly like an exponential or something like that. So, that is not linear. So, we should make sure that preferably it should be linear, but design errors will be there. So, this is what they have characterized. Ideally it should be 0, ideally it should be 0, but then there will be linearity errors while converting. So, this is the digital input code. So, they have converted into like 2 raised to 12, right, 2 raised to 12 bit, no. So, 4000 up to 4096 it can go, we have seen it. So, you have seen it here that it is a 12 bit DAC, correct. So, it can go up to 4096 levels, or the values can go from 0 to 4095. So, these are small things that you need to look at from the data sheet, okay. So, see the code is going from 0 to 4095. So, that is what they have done. They have characterized the linearity error and the differential linearity error. So, I hope that is clear to you. Then typical characteristics, that mid scale gauge, gain error. What is the gain error? Ideally the gain error, the gain should not be differing across the temperature. So, that you get same operation for different temperatures. So, they have characterized it with respect to temperature. So, you need to know these things. These are like technical documentation perspectives actually. So, for sense of completeness you should get fascinated when you see the data sheet. It may not be fully relevant to your circuit design requirements, but then you can see how much detailed they have gone into preparation of any technical document. So, because at later point if some issue comes up, they should always have data to back whatever they are claiming. If you are, let us say you are studying now, you will later join a tech company that makes ICs or makes PCBs. So, and finally those PCBs or those products you will be offering to customers. when the you are actually a product seller finally, so you are offering it to a customer. So customer will, while deployment in their field, finally they will face some issues, they will come back to you. At that point you should always have data to support you as much as possible. Maybe there might be some situations when that scenario, that particular scenario was never encountered, then it is okay. But then if it is a typical scenario, your characterization of that IC or your product within your premises of your company or your organization should be such that it is very exhaustive and rigorous. It's the word to be used is rigorous. You have to do rigorous characterization so that you can give confidence to your customers. If you are a product seller, or if you are even if you are in a research and development institution, your work should be of that quality. Okay, that's why they have done all these things. Then they have told R2R ladder DAC how it operates. So I will not get into the details of this. This has been covered in the theory portion. So R2R ladder DAC, how it will work, and how the digital inputs are given like this from here, and then the analog voltage is generated. Okay. Then they have given, so what is the code, what is the value of the code, and what will be the V out. So value of the code can go from, we have seen, right, it is a 12-bit DAC. So from 0 to 4096 it can, for 4095 it can go. And as we have seen before, when we initially we saw, right, how do we convert the 3-bit binary value, we have to multiply it with the reference step, no? So that voltage is there, and then you get the output voltage. Cool. So that is what happens, and then you can always amplify your output voltage to get the output signal with the necessary ranges. Then after that, one major section of the datasheet will be application information. So here what they will do is, they will identify certain typical applications of the IC, and they will give you sample circuits which you can use, okay, sample circuits which you can use to see how you can implement that circuit. So they have to like stability circuit for current to voltage design, current output and the connection. So they have gain peaking prevention circuit with compensation capacitor. So they will prevent the peaking of the gain, okay, and then amplifier selection. So these are all peripheral things actually for your output amplifier. Okay, let us not go into the details of this. Then positive voltage output. So as we have seen, the output of by design, the output of it is negative. So what do you, if you want to make the output as positive, what you should do? That circuit they have given. You can always go through it in detail. Then bipolar output selection, that is like you want to have a bipolar output, like plus or minus. So output voltage will, so see here the full scale produces output voltages of V out equal to minus 2.5 volt to plus 2.5 volt. Ideally we would see, by default we would see only voltage from 0 to 5 volt or 0 to 15 volt, but now if you want to have a bipolar output, that also you can do with this circuit that they have shown. If you implement this circuit along with the IC, this is the IC, and then you have to add peripheral other op amps into that IC, make a circuit like this, and then you can have bipolar output operation. That is what they have told. So if you take any data sheet, they will give you these typical applications. So this is what you have to see. This will help you a lot in two things. One is, if you are confused or stuck as to what exact circuit to use for your typical application, most of the time that typical application will be there in the datasheet, and you can borrow from it and then make minor modifications as you want. Another one is, you will be able to see applications which you never even thought of with that IC. So this it forms a part of your learning curve also. So you can learn it. So you can learn new circuits. So this is an analog circuits course, and that too with a very high practical design aspect to it. So that is why we are covering these things. So this is one place. One part is us teaching you what all circuits that you can go through and what all circuits you can read. Another part is us empowering you and pointing you to how to enrich yourself better, cover more things, acquire more knowledge, and where to look for it. That is even more important actually, which not many people will tell you. So you can always open any data sheet when you are bored, just open data sheets, go to typical applications, you can always find new circuit applications for the same IC. So this is a very important value addition. Okay. See another one, there is a programmable current source circuit. So if time permits in the course, we might even go through one of these circuits with the board. Okay. Okay, then parallel interface, So that is all. With this the datasheet almost gets over. Okay. Then once if you want to buy the IC, you will have package information. So they will have the orderable part number for the device, what is the package, okay, what is the this thing environment plan, is it RoHS compliant. RoHS is like it should not produce any radioactive hazardous substances, that is RoHS. So it is green, and what are the things, so that they will show. And then once, and the last part of the datasheet usually is the package information. This is mainly for people who want to make the PCB with the IC footprint. If they want to create that like that I have shown, they will give all the engineering drawings of the packaging. That is what this is about. So you will see all the engineering drawing, how the package is, how it will come packaged, is it tape and reel or it's a roll, those things. So these are the pins, what is the pitch distance between the pins, what is the overall package dimension, what is the angle of the pins, how does the pin sit on the PCB, all these things they will show. So these are more important when you are finally making the PCB, but if you already have a board, you need not look at these things, you can just directly go ahead and test it, taking into account the functional characteristics that are mentioned in the datasheet. But this is important if you are making footprints and or making a PCB on your own, which you will be doing at some point in your career if you are interested in analog circuits. PCB design in analog circuits is a separate course in itself, and so this is this comes under that. Okay. So those all the engineering drawings will be given at the end of the datasheet. Fine. So that is it, we have finished covering the datasheet in like very short time. So these are the main things. I think you got a very wholesome idea about how a datasheet looks like. Now let us quickly write down what in your mind. So I will also not go back to the datasheet, but we will quickly write down what are the main things that we have to look for in a datasheet, like I told before. So first thing, features, what are the main features? So that will be the first section. So you will see what are the operating voltages, what are the operating voltages, what are the operating voltages, what are the input voltage range, and other specifications, like we saw, right, 12-bit, it is a 12-bit DAC, all those other specifications. Okay. Then features, then what did we see, then what will be there, another thing that will be there is applications, what are the broad areas where this IC can be applied, this is also very useful. Okay. Then what we have to look at is package, pin out and pin description. This is the most important, I will put an asterisk, this is most important when you are opening a datasheet. Okay. Then is typical application, which is very useful for your circuit design. And fifth one is engineering drawings. Okay. Only these 5 things you need to look when you open a datasheet. Just you can note this down. Open any datasheet, you just need to go through these things, and then you can immediately do either debug the circuit that you have in your hand or start going ahead and making a PCB on your own. So let us, with this in mind, with these 5 things in mind, let us just quickly go through the datasheet again in like under 2 minutes. Okay. So what all are there? So we go to the first page. Okay, features are there. What is the main description? Features. Okay, we will see the features. Yes, these things are there. Fine. What are the applications? What are the main applications that you should look at? Fine. Then you can quickly go to the package. Okay, this is how internally it will look like. You will already be having some idea about how the circuit works when you go ahead to explore ICs that you need. So just you will roughly get an idea of what it. Okay, it is using R2R ladder to convert DAC. Fine. Then you come down. Then you have to see the maximum ratings. This also comes in the features. Okay, I should not go beyond these voltages. Fine. I should not store at this temperature, and I should not operate beyond this temperature. Cool. Then immediately you go to these things, only look at important things like reference voltage, operating VDD and all, then that will be done. Then quickly go to the, after that main thing is what? After that main thing is the package and the pin out. What all pins are there, what are their functionalities, or what you should connect to what, and that is it. Then pin out will be done, correct. Then you can glance through these curves if at all something you find interesting, correct. Then you need not spend much time in these curves, you can just quickly go through it. Then you can look at the typical applications, theory of operation, which also you would already be knowing, but application information will be something new to you. You can see typical applications and see if they have already given some typical application that you can borrow for your design, and then go through the typical applications, and then finally what is the part number you want, and then what is that the engineering drawing you have to see what are the dimensions if at all you want to make a footprint on the PCB. So, this is the data sheet of so we covered it in a general point of view to see how you can cover a data sheet. Okay. So, see it in under 1 minute we have seen quickly. After we spend some time we understood what to be looked for in a data sheet and what is to be just glanced through, and then this way you can cover any data sheet you want in a very quick time. Okay, in 1 minute, because if you are in a company or if you are working with an organization, if you are into research, you will not get that much time to go through each and every word that is written in a data sheet. You just need to know what to look for, where to look for, what are the important things to focus. Once you know that, you can quickly finish it off. So, this is the IC that we are looking at, DXC7821. Now, next we will look at the board and we will give digital inputs and see what are the analog outputs coming, and see if whatever we have been discussing to understand what all are the details. Let us see if actually it is working on the board, so that you will get the sense of completeness.